What specific problem does Cut Cross-Entropy (CCE) aim to solve in large language model training, and how does this problem affect memory consumption?
Cut Cross-Entropy (CCE) aims to address the significant memory consumption associated with the cross-entropy loss layer in large language model (LLM) training, which can account for up to 90% of the memory footprint. As LLMs utilize larger vocabularies, the memory required for the log probabilities generated by the cross-entropy layer increases dramatically, leading to excessive memory usage, especially in models with large vocabularies like Gemma 2. CCE reformulates the cross-entropy computation to depend only on the log probability of the ground truth label, allowing for a memory-efficient implementation that avoids the need to materialize a large intermediate logit matrix in GPU memory. This results in a negligible memory footprint that scales with the number of tokens and vocabulary size, rather than the product of both, thus significantly reducing memory consumption during training. Overall, CCE enables larger batch sizes and more efficient training of LLMs without compromising latency or convergence.
How does the proposed Cut Cross-Entropy (CCE) method work? Illustrate the steps involved in its computation clearly, especially regarding the reformulation of the cross-entropy loss and the role of the log-sum express operation.
The proposed Cut Cross-Entropy (CCE) method reformulates the cross-entropy loss by focusing on the computation of a single log probability corresponding to the ground truth label, rather than calculating the full logit matrix for all vocabulary entries. The computation involves two main steps. First, an indexed matrix multiplication that combines the embeddings of the input tokens with the classifier matrix, yielding a vector of scores for the ground truth labels. Second, a log-sum express operation is performed over all vocabulary entries, which is independent of the next token being predicted. This reformulation allows CCE to avoid materializing the large intermediate logit matrix in GPU memory, instead computing logits on the fly in SRAM using custom CUDA kernels. The result is a cross-entropy computation that maintains a negligible memory footprint while ensuring efficient forward and backward passes, thus optimizing both memory usage and computational speed.
Can you provide a simple yet illustrative example of how CCE computes the cross-entropy loss for a given token? Describe the main algorithm steps and the inputs involved in this computation.
Cut Cross-Entropy (CCE) computes the cross-entropy loss for a given token by reformulating the loss calculation to minimize memory usage. The main algorithm steps involve first calculating the log probability of the ground truth label using an indexed matrix multiplication, which combines the embeddings of the input token sequence with the classifier matrix. Specifically for a token, x_i, CCE computes the loss, L_i, as a vector product of the embedding, E_i, and the classifier, C, for the ground truth token, while the second term involves a log-sum express operation over all vocabulary entries which is independent of x_i. The inputs to this computation include the embeddings, E, for the token sequence, the classifier matrix, C, and the index of the ground truth token. By leveraging on-chip SRAM for intermediate calculations and avoiding the materialization of the full logit matrix, CCE achieves a negligible memory footprint while maintaining computational efficiency.
What are the theoretical and practical benefits of using CCE over traditional cross-entropy implementations? Provide specific metrics or advantages related to memory usage and computation time based on your findings.
The Cut Cross-Entropy CCE implementation offers significant theoretical and practical benefits over traditional cross-entropy methods. Theoretically, CCE reduces the memory footprint from O(n) times V to O(n) plus V, where n is the number of tokens and V is the vocabulary size, allowing it to scale efficiently with larger vocabularies. Practically, CCE demonstrates a peak memory usage of only 9,631 megabytes for a batch of 8,192 tokens with a vocabulary size of 256,000, compared to 28,000 megabytes for the baseline implementation. In terms of computation time, CCE computes the loss slightly faster, 5% faster, than the fastest traditional method torch, compile, and achieves a 6% faster computation for the loss and gradient combined. Additionally, CCE leverages gradient filtering and vocabulary sorting to skip unnecessary computations, leading to a 3-5x speedup without loss of precision, showcasing its efficiency in both memory and processing time.
How was the effectiveness of CCE validated in the paper? Discuss the experimental design, datasets used, and performance benchmarks that were employed to assess its performance compared to existing methods.
The effectiveness of Cut Cross-Entropy, CCE, was validated through a series of experiments that compared its performance against existing methods, specifically using the Alpaca dataset for inputs and labels, and the Gemma 2-2b model for computation. The experimental design involved assessing runtime and memory usage for a batch of 8,192 tokens with a vocabulary size of 256,000 and a hidden dimension of 2,304. Performance benchmarks included comparisons of peak memory usage and computation time across various implementations, such as the baseline in PyTorch Torch, Compile, TorchTune, and Liger kernels. Results indicated that CCE achieved a negligible memory footprint that grows with ON plus V, contrasting with the ON times V of the baseline, while also computing the loss slightly faster than Torch. Compile by 5%. Additionally, CCE demonstrated training stability, with loss curves indistinguishable from those of Torch. Compile, confirming that its gradient filtering did not impair convergence.
What limitations or constraints does CCE have, particularly concerning its applicability or performance in different scenarios? Discuss how these limitations might influence the choice of loss computation method in practice.
The Cut Cross-Entropy, CCE method has certain limitations, particularly in scenarios where the ratio of vocabulary size to hidden size decreases, as it may lead to slower computation times compared to other methods for loss and gradient computation. While CCE excels in memory efficiency, its performance can be impacted by the absence of vocabulary sorting and gradient filtering, which can increase computation time significantly, up to 3-4 times longer without gradient filtering. Additionally, CCE's reliance on the sparsity of the gradient means that in cases where the vocabulary is less sparse, its advantages may diminish. These constraints suggest that while CCE is highly effective for large vocabularies and high sparsity, practitioners may need to consider alternative methods when dealing with smaller vocabularies or when computational speed is critical. Ultimately, the choice of loss computation method will depend on the specific characteristics of the model and the training data, balancing memory efficiency against computational performance.